I want to talk about what type of air conditioning systems and what I want to look at is evaporative cooling. Evaporative cooling. So in evaporative cooling, what you're going to have is you're going to have a duct of some sort. And inside that duct, you're going to have a soaked, something in here that's soaked with water. Maybe it's a fabric pad or something like this. You're going to soak this with water here. So this is going to be a soaked fabric. Okay. And what you're going to do here is you're going to bring in moist air, and it's going to be the mass rate of air and the mass rate of vapor and some temperature 1 and some omega 1. Okay, and you're going to flow that over that soaked fabric. Okay, now what's going to happen when you take that moist air and you go over that soaked fabric? The air is going to want to take some of that water and evaporate into and put it into solution. Okay, and so when you come out the other side, your temperature 2 is going to be less than your temperature 1 because energy from that air is going to be required to evaporate some water out of that fabric. And then, of course, your omega 2 is going to be greater than omega 1 because now your humidity ratio is increasing because there's going to be more massive vapor into that air. Okay, so key points here: energy is required for evaporation. Okay, the moist air increases in moisture content, in water content, in water vapor content. And here's the very at nearly a constant wet bulb temperature. Okay, this is very important. Sometimes on your psychometric chart, you're like, how do I deal with this? How do I work with this problem? Well, we're going to say this process, when we're looking at our psychometric chart, and we're looking at point 1 and point 2, it's going to be at a nearly constant wet bulb temperature. Okay, that is going to be what we're going to be doing here. We're going to be on that line. Now, in actuality, you might vary a little bit, but for all intents and purposes, this is what we're going to be using. Now, evaporative cooling, you're not going to want to use evaporative cooling in Manhattan, Kansas. You might use evaporative cooling in a drier climate. So, for example, I grew up in rural western Kansas, a town called Lakin. It was very dry. 100 degrees out there was 100 degrees. There wasn't a lot of humidity. And so I remember my grandparents had we called it a swamp cooler that we would attach to the garden hose in the house with this big fabric mesh-like pad that was covered in water, and it cooled the house, but also humidified the house because it was very, very dry heat out there, and so we felt comfortable. Maybe the house before was 85 degrees and 10% relative humidity, and now we moved it up to we lowered the temperature to 75 degrees, but moved the humidity up to nice. But you don't want to increase the humidity of a house in Manhattan. It's already very, very muggy. You don't want to have it now. It's cool, but it's also just sticky inside the house. So dry climates that you want to do this on. You will see these a lot in Colorado. If you go out to Denver, Colorado, you're going to see a lot of these type of coolers that are on the surface or they're on the roofs of a lot of houses where they're going to do this. You go to Louisiana, you're not going to want to do something like this. So there's different places, different types of cooling mechanisms are going to be better for different places. Okay. Let's talk about the opposite of that. Let's talk about, because this is really adding water to the air. Let's talk about, adding water to the air. Let's talk about other types of humidification. Let's talk about other types of humidification. My brain's a little scrambled today. Okay. There's different ways to humidify the air. Okay, let's just say we're now dealing with a heating situation. Usually humidification is going to happen in heating. I just explained how humidification can happen when cooling, but that's in a dry climate. All cold air is going to be very, very dry. And so if I have a duct here that I'm going to be dealing with, And I have moist air coming here. And it's temperature 1, omega 1. And it's coming out of here. We have moist air coming out. Okay, it's at temperature 2. And here I want to make sure the omega 2 is greater than omega 1. I want to make sure that's happening. And what I'm going to do for this is state 1 and this is state 2, I'm going to do that by injecting H2O. Now, there's two ways I can do this, and I've talked about this already. I can do this by putting steam in, hot, vaporous H2O, or I could put liquid water particles in there. Okay, so let's look at what this would look like on our psychrometric charts. Okay, so here we have, if we had steam. Okay, if we had steam, what's going to happen if this is our psychrometric chart? And let's just say we're at this point here. This is our point 1. Humidification is going to bring us from our omega 1 to some omega 2. But it's also going to increase our temperature, so we're going to go this direction. This is the direction we're going to go from omega 1 to omega 2. Okay, so what we have here is omega, and the temperature of our dry bulb, they both go up. Okay, temperature 2 is greater than temperature 1, and omega 2 is greater than omega 1. Okay, so we humidify. We're also heating with that. That steam is added to heat. If we have liquid water that we're dealing with here, liquid, here's our vapor, our psychrometric chart, and here's our point 1. We're still going to go from omega 1 to omega, we're going backwards. Okay, because now energy from the air is going to need to go and evaporate that liquid water. So here, the temperature dry bulb is going to go down, while the humidity ratio goes up. Okay, because here we have the energy needed to evaporate water vapor, liquid water into water vapor. Okay, so there's two ways to humidify. So what you have to choose is, how are you going to humidify in your house? What are you going to do? What's the method? And as engineers, that's a decision that you are going to have to create. Okay, so those are the two real processes I want to think about. There's a lot of other things that we are going to be working on, and a lot of other examples that we'll be working on, but I think those are unique examples, and they kind of tell us about which path we might go on our psychrometric chart. Okay. The other thing you need to know is this. When you go over, in an air conditioning system, when you go over a set of cooling coils, okay, this is our cooling coils here. There's a refrigerant going here. Maybe it's a mass flooded refrigerant. Maybe it's R134A, okay, coming through these coils. Over those coils, it's going to see those coils as that microclimate that's probably below the dew point. And what's going to happen is that there's going to be falling out of here. You're going to have condensation come on top, on the outside of those coils, and then liquid water is going to drip off of these coils here, and this is going to be your mass flow rate of your water coming off. Liquid water is going to condense at the dew point. Okay, and so right after this, if we consider this point 1, the point 2, right after those coils, what you're going to have is saturated air coming out. Your humidity ratio, sorry, your relative humidity at point 2 is going to be 100%, and temperature 2 is going to be less than temperature 1, and your humidity ratio 2 is going to be less than your humidity ratio 1. Anytime liquid water is added or removed, you're going to have a change in your humidity ratio. Okay, so that's what we're thinking about. We need to think about how that liquid water is added or removed from any system that we're dealing with. Okay, and so if we were to draw this on the psychrometric chart, might be up here, bringing in hot, moist air, and then we're going to be cooling it down at a constant temperature until it hits saturation. Okay, once it hits saturation, now we want to still cool it. Okay, maybe we want to cool it over here. The only path we have is going down this saturation curve until maybe we hit right here. Okay, this is going to be where our temperature 2, what we're going to consider our temperature 2. We're going to consider that our liquid water is going to be all dripping out at this. Now at all these different temperatures here, for our calculation, we're going to say that all the water is coming out at temperature 2. Now, this is colder, but very humid air. It's 100% relative humidity, and you don't want to push that back into your house. But that's what is coming out at state 2. That air then goes through the ductwork. In that ductwork, it heats up just because the house is warm. It's going to heat up that ductwork, the air in that ductwork, and it might move us our temperature 3, which is going to say we're going to decrease the humidity ratio, and also we're going to decrease the dry bulb temperature. Okay. Usually, if you want your house to be at 75 degrees, you're going to be blowing air about 20 degrees Fahrenheit lower into that room. So what's going to happen, that air is going to come out, it's going to mix with the air, kind of mix together and produce the temperature that you want. Of course, you're sucking air out of the room. That's called return air. You'll find a return air vent someplace in your house. That's the air that's coming into the air conditioning system. It goes through the air conditioning, cools out, and then blows back into the room. So it's a kind of a cyclic process. You're going to have, I said cyclic process. All the words sound weird out of my mouth today. But you're going to have air coming in through your window, sealed things. Temperature in the warm climate you're going to have, or in a heating situation, you're going to have hot air seeping out into the surroundings, because a lot of things we're going to have to deal with. And if you took a class about heating and air conditioning, we would deal with all these things as we would do a more detailed discussion of our air conditioning system. But in order to help us understand this better, I'm going to do an example problem today, and I'll do more example problems for the rest of the week. So we'll end this and we'll go and do one example problem.